اوكي. بسم الله الرحمن الرحيم، الصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Uh, so last three lectures of the course. So this one will be on the impedance control and continuing what we discussed last lecture. Next week, Sunday, inshallah, we're going to have another lecture on whole body impedance control for floating base manipulators. And then the last lecture, which is next week, Tuesday, inshallah, it will be an open discussion, so you can discuss anything you want. I'm gonna ask you for feedback on the course, not the online feedback, more detailed technical feedback, because as you know, this is the first time this course, so your feedback will be extremely important. And then we're gonna have one more lecture on Sunday, which will be the project presentation. Okay, the project deadline for the reports will be on Thursday, so next Thursday. Okay, so not a lot of stuff to remember. Okay, so it's easy. So the lecture question. Okay, today's lecture and next lecture. So the coming two lectures, this one and the next one, will have a different flavor. They will have minimum math, no math. I'm not saying no math. I'm saying minimum math needed, without all of the details inside, because I want to cover as much as possible to expose you to these different topics. We're really at the end of the course and at the top of the stuff that's most relevant to applications. So implementation of these algorithms or of these details, again, actually just to cover, you're going to see how much details I'm going to be like skipping, and I'm going to be providing for whoever is interested to read more on that, some supplementary material that you can look at your own pace or whenever you want. But this is the level of, so the same level also for your studying. So the same level of depth I'm going in today, this is the same level that you need to be at for your exams, okay? So anything I skipped here, for the exams, don't try to look for it. If you want to understand more, you'll be provided with supplementary material for reading, okay? Today's lecture will be continuing with the impedance control. I want to give you a flavor of what does it mean to have this controller, what are the different, again, as I mentioned last time, this paradigm shift. And let's jump immediately into the recap of last time. So the interaction control, what we discussed last time. So the paradigm shift is that we're not interested in controlling the pose of the robot, of the end effector in this case, or the wrench it's applying to the environment. We're not thinking in terms of signals, that I want to control this signal and I want to have a controller that's implementing this signal or like implementing this control law. But what we're actually thinking in is that we want to control the behavior of the robot. How is the environment, okay, which is unknown to us, how does it see the robot from its perspective, okay, from its port, as we discussed last time. And these are typical examples that you see for interaction. And the main control techniques we're focusing on is impedance control. So this was introduced by Neville Hogan. It's in 1985, if I remember correctly. And the whole idea is that we want to design the controller. We want to design the controller such that the robot and the controller, so the closed loop system, seen with respect to the environment's side, with respect to the environment's port, it sees it as a mechanical impedance. And what is a mechanical impedance? It's simply a spring and a mass and a spring and a mass and a damper. Okay, so a mass spring damper system. And by shaping this dynamic behavior, then we will indirectly control the force that the robot is applying to the environment. Okay, so this is the idea that the impedance control, the basic philosophy of it. Today, we're going to be looking at what are the control law that we implement. Okay, so the control laws again, as you're going to be seeing, will be compact for an N-link manipulator. But again, there's a lot of details inside that it's manipulator specific, and we're going to point out these today. This is the basic idea of impedance control for a point mass. Again, what we start with usually. So we have the kinematic equation and the dynamics of a point mass. We have some control forces that we want to design such that the point mass is able to interact with an environment. And when it's interacting with the environment, there are interaction forces applied to the point mass. The goal of the impedance controller is that the closed loop system, so the controller and the mass, so the spring and the mass here, these are all virtual springs and virtual masses. So they are whatever the controller is simulating the system to be behaving. Or in other words, it's emulating the system such that there's a virtual spring and a virtual mass. The mass is the only thing that's that's physical, right? And we're applying directly to it some control forces, and the environment is physical, but the spring and the mass, they are virtual. So we want the whole system, the virtual parts and the physical part, to behave as if it's a mass spring damper system, okay, with respect to the F the interaction forces. And the Q here is some sort of the deviation of the spring, so that's like the elongation of the spring. So it's the difference between the one end of the spring, which we have as the desired set point. It's a virtual desired set point because I don't want the robot to go to that set point. If there are no interaction, it will go to that set point. But if there is an interaction, I want to design the behavior such that this is a spring. And the other side of the spring is the actual mass, is the actual position of the mass, which is the psi. Okay, so this is in these are equations that they hold in 1D, in 2D, and in 3D. Okay, as long as we're only thinking of a point mass, you can expect things to become nasty when we discuss what the orientation, right? So this is only the position. When we look at the orientation, things will get nasty. Okay, but so far this is what you should be familiar with, a mass spring damper system. So if this is my system and this is what I want it to be, what is the control law? It's very easy to deduce it. Okay, so the control law is very simply this expression, where I'm adding a feed forward term depending on the desired acceleration that this frame is moving with. So this end point of this virtual spring, and I have this damper. This is simulating a force due to the damper, and this is simulating a force due to a spring. Everything is linear here. So this is a linear spring, linear damper, and this is a feed forward term. Yes. This is the impedance idea. So mechanical impedance. So this is an equation that it takes force it takes the Q as an input, right? It takes Q dot and Q double dot. It takes the motion as an input, and it produces the force as an output, right? This is exactly the whole idea of impedance. This is the definition of impedance, right? It's the ratio between motion and forces, velocity and forces, okay? So this is with analogy to electrical impedance. Electrical impedance is also the ratio between current and voltage. Okay, so this is the intuition behind it. And again, so how did this inspiration come to Neville Hogan's mind? He thought in terms of the other way around. He thought of that environments usually have an admittance causality. Environment usually take velocity as an input and give you force as an output. Okay, and thus the controller should behave in such a way, or the robot and the controller should behave in such a way such that it takes the force as an input and give velocity or the motion as an output. So this is the whole idea. If the environment is in admittance mode, then the robot should be in impedance mode. We're going to have a different way, and this is the last part of this lecture, where the environment can be in impedance mode, so the controller should be in the opposite, admittance mode, and this is called admittance control. Okay, it's the opposite. They're going to be I can spend some time talking about it, but I'm going to show you some nice videos in the end that will make hopefully the idea clear. Okay, yes. Why? Why is this a disadvantage? That's right. Okay, the stability of the system depend. If you look at this controller, we are feedbacking this term and feedbacking this term, and we have this term only as a feed forward and this term only as a feed forward, right? If you compare this to the PD control, you're going to find it's exactly the same with feed forward terms. Feed forward terms will not affect the stability, okay, of the system, and the rest we know it's actually asymptotically stable. It's globally asymptotically stable, right? So we already know that the system is stable. But the problem is that the stability depends also on the interaction forces. Because even if this part is stable alone, and when we study stability, we don't consider any interaction forces. We consider this to be zero, and this is the closed loop dynamics. So what if we have interaction forces? And this is where we are not going to be using the standard Lyapunov stability, but not an extension, but a different, again, way of thinking about stability, which is called passivity. I'm not going to be discussing passivity at all. I'm going to give you a nice, I think 300 or 400 page book if you want to read about it. Okay. So now let's look at how impedance controller is implemented for manipulators. So we're thinking now of mass so the linked serial linkage, so multiple rigid bodies connected together through joints, and then we have this reduced dynamic equation. We have the inertia, we have the centripetal and Coriolis terms, and we have some friction in the joints, could be nonlinear, and we have the gravity. We have the control torques, and we have the interaction torques. The interaction torques, they are just an image, or they are due to the effect of whatever the end effector is experiencing at the tip. We can also have interaction at any joint, by the way, or at any body. So for example, if this is the robot arm, I can push it from here, or I can push it from here. But we're assuming that this is not interacting with the human. So it's the robot itself is going to move, and it's going to hit something or interact with something at this end effector. So that's why we consider only interaction forces this way. Yes, ma'am. Opposite in terms of the sign. Why? So these are the equations, and these are the torques applied by the motor. Okay. So you're saying this should be a minus sign. Yeah, I think you're correct. Yeah, I think there should be a minus sign. If these are the interaction torques applied by the robot to the environment, right? But we can think also in terms of the interaction torques due to the wrench applied by the environment to the robot, and there's just a minus sign in terms of a wrench, right? So Newton's third law. So I'm not gonna. I think here I say is I see there are torques due to the interaction. I didn't specify here which is applied to it, but again, you can infer it in details if you want to write it precise. But you're correct. Yeah, just for simplicity. So it's either I can write tau internal or tau minus tau internal. Just how you define this torque. In both cases, whether with a plus or a minus, they usually come from the Jacobian. So the Jacobian is what maps the interaction wrench at the end effector. So in the end effector frame. So I can be pushing this object from here, from here, from here, from here. It doesn't matter. And all of these, okay, it's in the same interaction because it's applied to the same body. And I can represent this interaction wrench, which again has some torques and some force components in this end effector frame. If you do that, if you represent this wrench in the end effector frame, what are the corresponding torques? They are given by the Jacobian transpose. And the Jacobian itself is the map that will map the rotational velocity, so the angular velocity of the joints, to the end effector twist. Okay, so you can think of this. So this is the duality. So here, this is velocity, and this is the 6D velocity. So this is ND velocity of the joints, and this is the 6D velocity of the end effector. This is the 6D force at the end effector applied to the end effector, and this is the corresponding torques that come from it. Okay, is that clear? And as was just mentioned, that usually in papers they don't even say that these are torques. They just write that this is the Jacobian transpose multiplied by the end effector, and you can infer that these are torques. Okay. Let's look at we discussed the geometric Jacobian, but we're going to be using it today a lot. So I just want to remind you of some of its how important it is. We actually didn't dive deep into it. We could have spent, I think, a couple more lectures on just the geometric Jacobian and how we can use it to design the robot itself. But you can read about it in the book. So the geometric Jacobian, as just mentioned, it's the map from the angular velocities of the joints to the rigid body twist, right? So the last rigid body, the end effector twist, which has some angular velocity components and some linear velocity component. You can see that the Jacobian is always a map from whatever is happening at the joints, so the dynamics of the joints, or the kinematics of the joints, and to be precise. So these are the kinematics of the joints, and these are the kinematics of the end effector. The end effector, whatever the robot is seeing in the end effector, is usually called the task space. So the joints, they live in the joint space. So it's a motor that changes all of these joints, but the end effector lives in what's known as the task space. This is usually where you're going to be putting an object you want to manipulate, you want to open a valve, you want to draw something. This is usually called the task space. Each column of the Jacobian, and we derived that earlier, I think it was lecture 12, or if I remember correctly. So each column of the Jacobian is nothing else than a screw axis the screw of each of our link manipulator for each joint. So it's the screw axis multiplied by some adjoint, which is just transforming this relative twist or this relative screw from the parent axis to the end effector axis. So everything here is expressed in the end effector frame. So this is S1 with respect to 0 expressed in E, S2 with respect to 1 expressed in E, and so on till the last joint. And the torques, they are with the transpose of that map. And more precisely, not just don't think of it as a map that's transposed. It's actually the dual of this map. Okay, so that we're mapping something from not from the vector spaces, but from the dual vector spaces. And in this way, the Jacobian transpose will tell us if there are some interaction that's happening at the end effector, what are the corresponding torques that are mentioned, that are felt at each motor. You're going to be seeing today that this Jacobian, we need to know it if we want to do any interaction control. It's extremely important also when we have human-robot collaboration or when we have teleoperation. Okay, so teleoperated with haptic devices and so on. This stuff is extremely important. So this is an extra bit just compared to the standard equations that we have. And the Jacobian, if you go back to the lecture 13 to 15, when we derived the scary equations of motion from the rigid bodies connected together and so on, these horrible, very scary looking equations, you're going to find that we had the Jacobian for free. So it's not an extra calculation. We already had it when we were deriving the big L matrix and the big S matrix, if you go back. Another very important thing about the geometric Jacobian is that allows us to to study or analyze the singularities of the system, the kinematic singularities. And this is a topic we never discussed, and okay, it's very important when we're dealing with, when you have manipulators. Whether floating base or fixed base, it's the same. This is a 2D example, so the same running example we had, the same one that you had in the assignment. You can go back to the code and you can play around with it. You can actually plot, you can actually calculate here the Jacobian. You're going to find it has this structure for this example. So this is particularly for this example, for the 2D link. So this is a 2D link and a manipulator. It's essentially a double pendulum. So it can only move in a plane, okay, in this plane. It can only do stuff like this. And we don't have any rotation around the X and the Y. So let's assume that this is the X, this is the Y, and this is the Z. We can only have rotation in the Z, but no rotation around the X and the Y, because this is not a spatial robot, it's just a planar one. And we don't have any velocities in the Z direction. So the robot cannot do, the end effector is always bound to the plane. It cannot go out of the plane. So we cannot have any velocities in the Z direction. So you see from the Jacobian, it's clear that no matter what the joint angles or the angular velocities will have, we will not get out of the board. Okay, we're not going to have any velocity in the Z, and we're not going to have any rotation around the X and the Y. Okay, so the Jacobian already says a lot about all of the possible movements of the robot. In case you have a more complicated thing, you can analyze. This is just with straightforward to look at the equation and see whether you can see it immediately from without doing any analysis. But usually you're going to look at the rank of the Jacobian and the determinant, and you're going to do some analysis and see all of these configurations where you're going to be having this. You're going to be able to move or all of the directions you can move in, and with the dual case, you're going to be looking at all of the forces, all of the force direction that you can actually produce from the robot. Okay, or in other words, these are all of the force directions that the robot can interact with in the environment. In other words, just as an example, if I have this robot and I wanted to push in this direction, can I have this? No way, right? The same also if you have a complicated 6D robot or a 7D robot or more than that, there are some directions in some configurations. You see the Jacobian is configuration dependent. So it changes when theta changes. So there will be some configurations that there are some directions I cannot push in. Right? So these are known as the singularities. Okay? So again, more on that. If you want to read, you're going to find some nice material, inshallah. Now what we want to do is that we want to look at, these are the equations of motion. Yes, Mark. We'll ask later. Okay. Because it will deviate us from the main topic. Okay. And we can discuss a lot, but not now. Okay. So these are the equations of motion without any control. Okay. In other words, we're going to be turning off the motor. All of the motors will be turned off. from your simulations, the people who had robots, what happens? It falls down, right? If you don't have any friction in the gears, or if you don't have any large gears that are preventing it from falling down. Usually, if you have like a position-controlled robot, you're going to have gears inside, and the gears will prevent it from falling down. But if you have what's known as back-drivable robots, then it's really going to be falling down if you don't have any of these gears. And in the simulation, you did not simulate all of these gears and the forces due to them. This is why it's falling, just so that you see what does that mean. If we are interacting, if we have some interaction wrench at the end effector by a user, by someone that's holding the robot and going to be moving it around while the motors are turned off, what will this user see? Or in other words, what will he or she feel at the end effector? Imagine that you have a point mass, and then I hold it and I just move it around. What am I feeling? Inertia. I'm feeling its inertia, and I'm also feeling that it wants to fall. If it's something that's heavy, it will pull me down. I'm gonna feel it. And if it's something that I keep moving around, I'm gonna feel that there is some resistance to the motion. And if it has some friction, maybe it has, I don't know, maybe it's some, I'm moving in air, and maybe it has a large area, and I start to move it, I'm gonna feel also the resistance of the wind, so the friction due to the wind, right? So all of these are stuff that you feel from the end effector. If we have a robot arm, and the user holds the end effector and starts to move it, what does he or she feel? Feels the inertia of what? All of the links, right? Because it's moving the whole manipulator, not just the end effector, all of the links. What else? It's friction, also the gravity. It's also experiencing the gravity torques. What else? And also the Coriolis terms. All of this will be felt by the user at the end effector. How can we write these equations in this with respect to the end effector? You remember this is important at this point because we want to represent everything with respect to the end effector, because there is where we want to have the desired impedance. So this is where we go, just so that you don't get lost. So what we can ask is that how does this equation feel like if there's someone that's interacting at the end effector, okay, at this frame, at the end effector frame? And to calculate the following, I'm not going to do the derivation. It's just going to take some time from us. It's available in the book. It's straightforward to do that. I'm just going to give you an intuition of how you can, what are the steps. If you multiply here by J inverse transpose, okay, so this will disappear. You're going to have J inverse transpose here, J inverse transpose here, J inverse transpose here, and J inverse transpose here. Easy? That's the first step. Theta dot is related to what? Is related to the angular, is related to the twist of the end effector. I can also derive this equation. I can also derive that, derive it in time. So I can also express theta double dot in terms of V dot and V and J dot, right? In the end, if you take all of these equations and try to replace all of the theta and theta dots and the theta double dots here with something that's related to wrench and twist dot, you're going to be getting in this equation. It looks like this. Just know it as like without the details inside. They're not important. I just want you to get the flavor of what do all of these terms represent. And you should know it. You should understand this even without knowing the details. So this is how it looks like. And the first term here, it is what's known as the apparent inertia. Okay, you are correct. It definitely the user will, so the user interacting here with the end effector of the robot will feel that there is some sort of inertia. Remember the equation of motion of one rigid body? We had here the generalized inertia of one body multiplied by V dot. Here we have a matrix, a 6x6 matrix that depends on theta. Why does it depend on theta? Every configuration will change the inertia. So some configurations I will feel that as if it's very lightweight, and some configurations like it will be very heavy. Okay, we can think of it this way. So the inertia, they depend on the theta. Then this is a nonlinear friction term that depends on theta, so on the configurations, but also on the V, on the twist. And it's multiplied by V linearly. So this is equivalent to a nonlinear friction. And this is the apparent gravitational forces. Okay, so all of the links want to fall down. So the end effector wrench will be equivalent to like these wrenches combined together. But again, they also depend on the theta. So what you see here is what's known as the dynamics of the manipulator in the task space. So all of what we've been discussing so far, so these equations, they are known as the manipulator dynamics in the joint space, but these are the manipulator dynamics in the task space. So this is what the end effector from its side feels the robot moving. Yes. Yeah.
Joint space is the same as configuration?
Yes. Joint space is the same as the configuration space. Yeah. Yes.
But J is like 6 by n meters.
That's right. That's a very good question. This is why this is an what we actually need to multiply here is some sort of matrix that will make this identity. So we want to actually invert this relation. It might not be invertible, that's for sure. Even if you have even if you have 6 links, there might be here some configuration that make the J and the J transpose non-invertible, and then I cannot calculate this. So actually I cannot talk about task dynamics if at the singularities. So if related to the discussion that I just skipped. So again, there are a lot of details here, but think of it in the simplest case when you have a 6-dimensional and all of the configurations that the robot is designed in such a way, in a perfect way, in a perfect world where we don't have any kinematic singularities. I can always do that, okay? And then I can see this equation. I can see this dynamics. So this is the equation that we have if we don't have any control. If we have some controls, this is what we're gonna be having. I just removed the control torques from the original equations, and then they came back with multiplied by J inverse transpose. Okay, so far so good. Now this is okay. So this is what the equation of motion is with respect to the end effector seen from the end effector's frame or port, and this is our desired impedance. And now we can do a mix and a match, and we can see what do we want to cancel, or what shall we choose the control torques such that we get this impedance behavior. So this was the whole idea. So this is just a turnaround so that, and we're doing the same what we did for the point mass. For the point mass, we wrote this dynamic equation, and we said we want the closed loop system to look like this, to look like a mass spring damper system. What should the controller be? We derived it from there. This is exactly the same. These are the equations of motion seen from the end effector in the task space. And we want it to be something like this. What does this resemble? What does this resemble? A mass spring damper system, but in what dimensions? 6. This is a 6 by 1. This should be 6 by 1. This should be 6 by 6. 6 by 6, 6 by 1, 6 by 6, 6 by 1. The wrench has 2 components. What and what? Torque and force. So I should expect this position variable to have what? Angular displacement and linear displacement. And this velocity to have angular velocity and linear velocity. What about this one? Angular acceleration, linear acceleration. So this is the equation I want it to be. I'm going to be discussing more on this later. But for now, take it as is. Let's assume it's as simple as this. It's not. So what is the controller? If we want that the closed loop system, the impedance behavior has something like this. Again, you can just compare. What will happen? I want this term to be equal to that term. But I want the first thing, what do we do? What do we need to do first? What do we do with all of these nonlinearities? We need to kill them out, right? Just cancel them. So this term will be equal to this and this and this inside of the controller. And we're left with something that's here. What do we choose it? We choose it with this expression with a minus, so that when it goes to this side, okay, it becomes with a plus. And that's it. So this is the control law. So this is what's known as the impedance control law that we can apply to any n-link manipulator. We don't have here the J inverse. You see, the J inverse was only in the calculation that we did. It's just like an intermediate step. But we can still implement the control law even if we don't have to be invertible. So that's no problem in implementation. Okay. It's just the behavior itself, or like the task dynamics will look differently, or we need to consider more because of the singularities. But in general, we don't need these singularities. We don't need to consider them at all. This is consists of two terms. You can see all of these terms, their whole purpose is just to compensate for all the task dynamics. Yes.
Well, the J inverse is already in that matrix, in that
This is the torque alone. So you can think of it this way. This whole expression should cancel this and should be equal to that. So what should be torque control alone? This multiplied by everything else.
That's done.
Yeah.
There's a J inverse there.
That's right. Yeah, that's correct.
For me to complete that in the first instance, I need to know the J inverse.
That's right. Yeah. Yeah. That's why I'm going to show you another example. Okay. So this is one way of writing it. There's a simpler way you're going to be seeing that. Okay. To answer, I think, your question. Oops. Yes. Question?
Like, since there's the J inverse, based on what you just said now, wouldn't it be cancelled by the J transfer itself?
Patience. Yes. Yes. Okay. You're spoiling my surprises. Okay. So this is the task dynamic compensation. Okay. And this is the desired impedance behavior. So I just should have these two terms in the control law. And if I do that, this will be the impedance behavior after I cancel everything, provided, of course, there are some conditions here. The first thing is that I need to measure all of these extra stuff. You see, we're not only talking about joints now, we're talking about stuff at the end effector. So I'm talking about position of the end effector. I'm talking about velocity of the end effector, the twist of the end effector. I'm talking about acceleration of the end effector. And in practice, they might not be available. So this is more, you see, the impedance control or the interaction control needs more information, not just the joint angles as we did with the PD control. Good question. The better question is, what is the difference between Q dot and the twist? Because both are velocity. Yes. Later on that later. So now, okay, so the surprise that Farouk and Muhammad spoiled is that you can, of course, rewrite all of these terms because they included the J inside, because they include the J transpose and the J inverse transpose and so on. You can actually rewrite it like this. So I can get all of these terms, multiply them with the J transpose, and rewrite all of the V dots in terms of the thetas and the double dot and so on. In the end, I get this equation. What does it look like? Exactly like what we did with the feedback linearization, right? So at least this part. This part is definitely a feedback linearization, right? I canceled everything here. I canceled the whole dynamics. And then I was left with something that I can choose, and I chose it with the J transpose and this 6D spring damper and mass system that we haven't talked about yet. Okay? But it looks like a spring and mass spring damper system in 6D. And we have here all of the equations that the dynamics I just killed, such that I get the behavior that I want, which is only this guy. It makes sense, right? I have a controller. Okay, when it moves, it has its internal behavior, its internal inertia, its internal nonlinearities, and its internal gravity. And for me for an outsider that's interacting with the robot to see it behaving completely different, I need to compensate for all of these terms. I need to know them, compensate for them, and then impose my dynamics that I want. Of course, this equation asks for a lot. Okay, in terms of information, in terms of like knowledge of the model. Okay, so the model information that you need to know all of the parameters that are inside of the M, the structure of the M precisely. You need the structure of the C and the structure of the B and the structure of the G and so on. So you see, that's a lot of information. I need to have a very precise model of the robot. Any misalignment between the axes, any center of masses that I calculated differently with respect to the real robot, all of this will not behave as what I wish. More importantly, also, I need to have the theta double dots being measured, and that's not easy. Usually what we have are angular velocity sensors, so encoders on a robot, and I can get the theta by maybe integrating them, that's okay, or using some extra potentiometer or extra displacement sensor. These are no problems, but differentiating these sensors to get the theta double dot with all of the noise, that's a problem. The same also here, the Q double dot will be something like an acceleration of the end effector in 6 dimensions. So I should also have some sort of accelerometer or something that measures the angular acceleration and the linear acceleration at the end effector. And that's also even if it's possible with sensors, but it will be very, very noisy. And I also need the velocity, and I need also the displacement of the end effector. You see, so this is all of the extra information. That's why there are some alternatives to this controller. One of them is to not to consider these impedance, so the inertia parts. So we can just neglect them in the controller. So one alternative is that we can write it like this. And this is one of the reasons. So this is one of the places you cannot just simply say I don't want to include this term and this term, okay? Because it will not work out. What you need to do is that this term is the one that you need to neglect, and this one, okay? So more on that later. But so again, this is one of the things that I'm not going to go into details. But this is the impedance control law. Not this one. Yeah, this is the one. So this is another formulation, another alternative to the impedance control, where we are not canceling the inertia and we are not imposing an inertia of our own. What does the robot see? What does the robot feel of the actual inertia that's happening? Let me go back to the mass spring damper example. So the 1D case. When we had the mass of the actual point and we added a spring and a damper, what did the end effector, okay, force see? It saw a spring and a damper, but what else? It saw the inertia of the actual physical system. If you go back to the equations, you're going to find there's the M and there's the B and the K, but the B and the K were in green because they are virtual, and the M was physical. It's the actual inertia of the robot. The same also here, because we didn't compensate for the inertia in the controller. What the robot will see at the end effector is the actual inertia of the robot. Okay, so this is the corresponding impedance it will see. And this is sometimes a problem if you want to have a very lightweight. So if you want to have the application to not have any inertia of its own, this is usually what people want in haptic devices. When we're dealing with haptic devices, it's actually a robot arm, but we want it to be as transparent as possible. I want to use it as a sensor, not that it has some inertia I need to overcome. Or if the robot is lightweight, sometimes in space robotics we have this lightweight, so the inertia, the apparent inertia that the end effector sees is actually very low. Another alternative, so this is another way that you can implement an impedance controller, and in this case we're going to neglect the inertia, and we're also going to not compensate all of these nonlinear terms for the same reason that we discussed in the feedback linearization, because they require too much information. The only thing we're going to be compensating is just the gravity. So you see that the impedance controller will be the J transpose multiplied by the gravity part, and they're going to have the damping part and the stiffness part. Also the inertia, I'm not going to be imposing it, so it will have some of the inertia of the robot, and it also have some of these nonlinearities inside of the impedance. But usually this will work very nicely if you have very slow interactions, where all of these terms can be very small, because these are quadratic in V. So if you have that the V is very small, these terms will be much less. And again, if you can play around with the math, you're going to be seeing, okay, I can rewrite it in the joint. And so this was in the task dynamics, in the task space, and this is in the joint space. What does this remind you of? Just look at it. You're going to see that this is the gravity compensation. This is like a proportional term, and this is like a derivative term. So in the end, we just go back to a simple PD plus gravity compensation equation. Okay. Yes. We didn't impose it. Yes, we said it's 0. No, we're not. We don't say that the Q dot is 0 because we want to have some damping. Otherwise, the damping will be only the damping that the robot has. We're not going to be modifying it with control. You remember when we had like the control of the double pendulum? We added damping. Even if there's friction, we added damping from our own so that we can control how fast it stabilizes. The same here. So we can add damping, even if it has damping of its own. We can add damping from our side, from the controller, so that it like goes fast or goes slow as we wish. We can control it. That's the idea. Any questions at this part before we move on? Yes, that's why. That's why it's very similar to it. And this is but this is the confusion. You see, this is the confusing part. We did not start by saying, I have an error, let's multiply it by a gain. We have an error dot, let's multiply by another gain, and let's try to see what the torque is. We didn't start from this paradigm, from this way of thinking. We started from looking at what does the robot see at the end effector. And because we did all of these simplifications, yes, we trivially reached a PD controller in the end, but thinking of it in the general way will allow you to extend it to more practical applications. This is the same idea as the same remark I made from last lecture when we said that a point mass controlled by an impedance controller is exactly the same as a PD controller. There's nothing there with some extra feed-forward terms. And because this is a very simple case, it's a trivial case, so you don't see the difference. But the way we extend both is completely different. Okay? Yes?
In cases we cancel the nonlinear friction and the inertia, we said it's the specific cases. I mean, one time it's a haptic or like low force robot, the second time it's flow robots. Okay, so I think these are too specific somewhat.
Yeah, they're too specific. Yeah, exactly. Then you need to do add more sensors.
Everything either from like the M and B.
And that's exactly what you have in haptic devices. So haptic devices, if they are really transparent, if you can really kill out all of its inertia to make it M as if it's zero, as if it's just a spring and a damper without any inertia, then you have to pay the price. You have to pay the price of having precise measurements and precise knowledge of the model and precise canceling of it and so on and so forth. Okay. And haptic devices, so haptic devices are like, you know what haptic devices are? I should have put a picture. Okay. Okay, so I can show you at the end, inshallah. Okay, what the haptic devices are. One last remark on the impedance control. So again, you see there are a lot of details I skipped. Okay? I just wanted to see the whole picture. And the details, you can look at it in your own application, at your own robot, and try to, you're gonna, hopefully, this will make sense when you look at an application. The last thing is this desired impedance. I said that, okay, this is what we want to have, but it should give you shivers. Because this is a wrench, and this is a 6D spring, 6D damper, and a 6D inertia. And you know that we don't treat inertia like that, right? We don't treat acceleration like this. We don't treat velocity like a dot of something. We definitely don't treat velocities as position as 6 numbers. So you see now that we need to do it geometrically. This will take us to 2-3 lectures. So I'm not gonna do that. Just to give you an intuition that what we did in the point mass is that we said that the Q is psi minus psi desired. This was something in R3. And we had a stiffness in RD in 3 dimensions, a damper in 3 dimensions, and everything worked out. So it was easy to derive this control. We cannot do the same, of course, for reasons you all know. I cannot say that Q is H minus H, okay? H of the end effector minus H of the desired frame. What do you have in mind here? H inverse multiplied, so this one inverse multiplied by that one will give you an error between both. What do you do next? If I want to get some spring due to a force, sorry, it's completely wrong. Force due to a spring on SE3, any ideas? Yeah. A what? No. If I want to have a spring, a virtual spring between 2 reference frames, one desired and one of the end effector. What? The geometric PD controller. How did we implement that? We said I have a potential function on this error, and I take the gradient of this potential function to be the torques. You remember what we did? We do the same. We're going to be saying that the wrench due to the spring is the gradient due to the potential on SE3. So I have a potential function on SE3, not a potential function on SO3 alone. I need a potential function on SE3. And I take the gradient of it with respect to the error, so the HED with respect to E, and then this will give me a range. Not directly, of course, I need to take the algebra into account and same tricks, okay? So this is just an intuition, and you can look at the papers that I'm gonna be posting, inshallah. Yes?
Yeah, in terms of the starting point, they're kind of different. But when dealing with it in terms of the potential functions, it's still the same thing.
That's right. But when you want to extend it, the other way we started by saying I have an error and blah, 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 blah. Here we think completely different. The extensions here are, okay, again, I can show, I did not tell you how to do it in the first place, the basic impedance control, so that I can tell you how to extend it. But if you want, we can discuss later on. Okay. Now time for some videos. Okay, so again, so there's no math. So there's little math, very little math. Okay, but hopefully the videos will make sense to you. So this is a nice guy that did these nice experiments, because it will cost us a lot to. This is, I think, $35,000. So I don't have them. We cannot buy them at the moment. Okay, so even if we do, I cannot bring it here. So we have these videos for free. What you see here is an impedance controller applied. What this guy is doing is that he's interacting with the end effector. So he's applying to it a wrench. He designed. Let me just stop it for. Okay, let's not do that again. So what he designed here is that he designed high rotational stiffness. If you have high rotational stiffness and you apply a torque, what does it do? It doesn't rotate, right? If you have something that's very stiff, right? If you have high stiffness, then it's almost as if it's rigid, right? Actually, rigidity is simply infinite stiffness, right? If you have something that's rigid, this means that if I press on it, it will not comply, right? And compliance is the opposite. So compliance, if you have something that has high stiffness, it means it has low compliance. So this is like the same idea of impedance and admittance, right? One is the inverse of the other. So stiffness is when we talk about impedance, while compliance is when we talk about admittance, okay? So here, what they're writing here is that they tuned the rotational part of this impedance that they want the end effector to behave as. They had high rotational stiffness, which means that it will not have any rotations. It's very stiff. It's almost rigid in the rotations part. But the translational one, they made it not that high, and that's why it's complying in the translation part. So this is what you see here in this experiment. So he's going to be applying only forces. But by the way, he cannot apply only forces. He cannot control his hand to apply only forces. There's always some torque component. But because the impedance behavior is very stiff in the rotational part, it's not rotating at all. You see? So the desired behavior that they want here is that the end effector only translates, doesn't do any rotations. This is what they have in mind in this experiment. There will be another experiment. So there will be another experiment now where they do high translational stiffness, and they're going to be allowing the compliance in the rotational part. I think it's now. Let's try to speed up. Oh, okay, shouldn't have done that. Okay, let's see. I think here it's yeah, okay, so this is the other experiment. So you see, the robot doesn't want to move. The end effector, in other words, doesn't want to move. It has a very high stiffness. It's almost rigid. And it's allowed to rotate. So the end effector can have rotations, okay? And it's not allowed to move. So we can change the behavior just by changing the value. Now let me come to a very good question that was asked last time, which is about trajectory tracking. What is the difference between trajectory tracking and doing impedance control? Because I can still move the reference frame. This is what happens. If I have pure trajectory tracking, any disturbance I get, what should I do to it? Reject it. But when there is a disturbance here, while I'm trying to do the trajectory tracking, what happens? It's just compliance. It complies to this disturbances, and then if the disturbance is removed, what does it do? Continues its task normally. So this is the change of mindset. Okay, you see it clearly here. So the robot still wants to do something, but the impedance controller is allowing it to deviate from the reference configuration if there's an environment, if there's an interaction. And this is exactly what we do when we're interacting with objects. We're not very precise. When I try to enter a key into a keyhole, I'm not doing very exact like position control so that the both of them are aligned, and then I'm inserting it. There's some compliance in between, and I just adapt my stiffness. We already have stiffness inside of our muscles, so this is our natural way of interaction. We are adapting our stiffness that we have in the muscles depending on the situation. Let me show another video. So this is my video. So you can do the same also on drones. This is a 6D. This is a fully activated hexarotor. It's one rigid body in the end. So a fully activated hexarotor just flying around means it's just a rigid body. The design of a spring here is simply there's a spring attached to the end effector to the virtual frame. The virtual frame is behind the wall. So what is the drone doing? It's pushing on the wall. What you see here are the force that is measured. So there's a force and torque sensor inside of the wall. So just to get the readings, and this is what you're going to be seeing here. So there is a force and torque sensor, and the more that the reference frame is pushed inside of the wall, the more force that the drone is applying to it. See, it's 8 newtons, now it's 10 newtons, and so on and so forth. At some point, the drone will push too hard that this propeller, for example, will stop turning, because each propeller, the thrust or the PWM that it should provide. How do we transform the control wrench that we have to this individual propeller speeds? This is the control allocation problem, okay, for those of those who have this in their project. The last thing in today's lecture is admittance control. So admittance control is the opposite. Impedance control has motion as the input, force as the output. Admittance has force as the input and motion as the output. If we have force as the input, what does that require as extra information on a robot? A force sensor. If you want to also do 6D force, so you all need to have what's known as a force/torque sensor. It's called a force/torque sensor. Another word would be a wrench sensor, but it's not used it's not technical. So if you search for wrench sensor, you're not going to find anything. That's why I just put it technically this way. So if you want to buy something, it's called a force/torque sensor. And if we can measure the interaction force, and this is the inverse relation of the impedance. If we can measure the interaction wrench, and we can calculate the desired acceleration of the end effector to be given by this equation. What does this look like? Actually, sorry, this computer, this should be a plus. Okay, sorry, a plus or a minus should be a minus. Yeah, it should be a yeah. There should be a minus. This should be a plus. Sorry, done in a rush. Sorry. So this is the acceleration. It's given by, I calculated from the inverse relation that I had for the mass spring damper system equal to the force. Okay, so I just invert this relation, and this is a force. I have it as an input. I have it from a sensor, and these are when I discretize this becomes like the next time step, and this is the previous time steps, and so on. So you can have this, or you can have it as with sensors also. I can have this as a sensor, so the desired acceleration would be the current configuration, the current end effector position, the current end effector velocity, and the current what I sense here with the force and torque sensor. I can also implement this without a force and torque sensor on the robot. I can do something called the disturbance observer or a wrench observer, and I can try to estimate this wrench using some extra algorithms, some signal processing algorithms. That's off topic. But in the end, if I have the Q double dots, these are my desired end effector location, I can use the inverse kinematics. And this is the first time I mentioned this, that this is one of the applications that you can have to invert the kinematics equation. We only talked about the forward kinematics, the map that it's given a theta, and it calculates the end effector pose. But now if I want some end effector pose and what are the corresponding theta, this is the inverse kinematics problem. So I need to solve it here to do admittance control. And you can transform the Q double dots to theta double dots. If you have a position controlled robot, you can use this directly, and you can apply it after integrating it twice. Or if you have some torque-controlled robot, you can use the inverse dynamics to calculate the corresponding torques given this corresponding theta, because the theta double dot and the torques, they are related by the dynamics. So I need to, you see, the admittance control is more complicated because I need an extra sensor or an extra information about the wrench applied to the end effector. I need to have perfect model of the robot. I need to invert this perfect model. The inverse kinematics is an optimization problem. It's not that easy. And then I need to do the inverse dynamics, which is even worse. But again, if you manage to do it, you're going to get some nice results. So this is a 6-degree of freedom robot arm. So this is the UR5E. So this is a universal robot. It has 6 degrees of freedom, which means that it's fully actuated at the end effector. You see the difference now compared to the impedance control. The user is changing the configuration of where the robot is. Okay. In the first one, he had very low damping. Here he's going to have high damping. So he's changing the behavior of how the robot is behaving, depending on the gains that he chooses. Okay. The robot can only comply this much, okay, because it's following the robot. It's not trying to push back. By the way, okay, the videos might seem exactly the same. The main difference is what the user is feeling. In the first, with the impedance controller, the robot is trying to actually pull. So when he moves it away from the impedance controller, he feels that the robot is trying to go back. In this controller, the user will not feel that the robot is trying to go back. It goes back naturally when he removes the force, when he removes the interaction. And this is why you need to take that into account. You cannot see it. You cannot see how he's feeling. But again, hopefully, okay, if you have one of the robots around and we can run these experiments, you can feel it for yourself. So we're talking about here interaction. So you need either sensory information or you have to feel it by yourself. And the last thing is, again, with quad rotors. This is a very old video, okay, by Raffaello D'Andrea. He did this a long time ago. He was way ahead of the field. But I want to show, sorry. He's going to be describing it for a broad audience. What the controller that's implemented for this behavior is an admittance controller. But I want you to hear his way of explaining how this quadrotor is behaving, okay?
It's a squat, for example. I'm trying to stay at a fixed point in space. If I try to move it out of the way, it fights me and moves back to where it wants to be.
So this is a standard PD controller, a standard stabilization controller.
We can use a mathematical model to estimate the force that I'm applying to the quad.
So this is the admittance control part. Changing the laws of physics is the desired admittance behavior.
Now have an intimate way of interacting with the machine. I will use this new capability to position this camera carrying quad to the appropriate location for filming the remainder of this demonstration. So we can physically interact with these quads and we can change the laws of physics. Let's have a little bit of fun with this. For what you will see next, these quads will initially behave as if they were on Pluto. As time goes on, gravity will be increased until we're all back on planet Earth. But I assure you, we won't get there.
So they're changing the gravity, you see? They're controlling what does the gravity that the robot sees. So they're controlling how fast it goes down by just changing the gravity, the desired gravity that the robot is simulating. That's it. I think there is a bit more.
They're the current members of the bring out the best. The choice to bring
That's
out
it, yeah.
people.
Yep, and that's it. So we have some time for questions. Yes, because when they play around with the apparent inertia of what, so we go back here. If I change here the inertia, then I'm changing how fast it accelerates when there is no force. So that's the idea. But here they're not compensating the gravity. So the idea here is that they're compensating part of the gravity. If they compensated the full gravity, it should not fall. But they're compensating maybe half of the gravity, or maybe 2/3, or they're choosing how much. Because if they compensate 100% the gravity, then it will fly. If they don't compensate gravity, then it's as if it's falling on Earth. If they compensate half of the gravity, they can change the behavior of it. This is another planet. So this is the intuition that he said. Okay, yeah.
Even the review, what is normal space? It was mentioned by you, maybe it's not specific, because it's 7 degrees of freedom. Mention null space.
Yeah, because it's a 7 degree of freedom robot, which means that for an end effector, I only have 6 dimensions. So now I have it's not a problem, but it's more that something that it's good in the robot, that for the Jacobian now is 6 by 7, right? It takes 7 by 6. It takes 6 by 7. It's multiplied by 7 angular rates and gives you 6 twist components. And the other way around, a wrench is multiplied by the J transpose, which is 6 by 7. 7 by 6, sorry, yeah, 7 by 6, yes. So the J transpose is 7 by 6 multiplied by the wrench, which is 6 by 1, gives you 7 by 1 torques. So you see, I have some redundancy. I can achieve the same wrench with more options for more solutions. If you have y is equal to ax, and x is 6-dimensional, y is 6-dimensional, a is 6 by 6, and it's invertible. So for every x, the map is 1-to-1, right, between x and y. For every x, I have only one option to solve, one solution for y, and vice versa. For every y, there is one x. But if you have an over-determinant problem, if I have more like a bigger matrix, so I want to solve, it will be 7 by 6, just one of them, so just not to confuse. So for a given 6 numbers, I can choose more options for the 7 numbers. What does this remind you of? When did we discuss this? Does anyone remember? Underactuation and overactuation for drones. Yes, exactly. So an overactuated drone, for example, like a drone with 8 propellers, right? Then I can in the end produce 6 numbers, which are the range, given the 8 numbers. But if I want to have a desired range, and I want the 8 propellers to behave to give me that range, I have more options. So the null space here is, okay, I can use this information. I can try to resolve the redundancy by trying to work out to use this, to exploit this extra degree of freedom. Okay, so now, and this is what I mentioned about the control allocation. The control allocation is actually an optimal optimization problem, and you try to resolve this extra degree of freedom in the optimization problem. But control allocation is off topics here. More.
This robotic arm is the same of BD controller, no difference.
No.
Because
no.
when we track it, the error is increased and the reaction torque is increased. To return it to...
Now, if you go here, and this is the secret on how much you're actually compensating. If they are implementing this control law, then you're true. Then it's true. It's equivalent to a PD plus a gravity compensation. And you're going to be feeling that, and this is the whole idea of the feeling part. What in this control, and this is something I didn't write here just because of the time limitations. I didn't write here. If we chose this control law, what would be the corresponding impedance? Okay, it will not be the same as this one. So if we go back here, the only way to get this impedance where I have my own inertia, my own damping, my own stiffness, that the user feels at the end effector, is to use this whole equation. If I didn't include this one and this one, something will change here. If I also didn't include that one, something will change in this part, and so on and so forth. Okay, so it all goes back to what the user feels. So you can only compare. All of them will have this behavior of wanting to go back if there is no force, and all of them want to return to the desired set point if you have an impedance controller. That makes sense. But how they go back, what is the behavior of how they want to go back? This is the impedance behavior. And this is what you can control. Yes. Impedance controller will be easier because it requires less information. What the impedance controller doesn't require is the wrench information. I don't need any information on the wrench here. I just calculate what the torques based on theta. I need here theta, V dot, theta, V, theta, Q double dot, Q dot, and Q. And the Q will have some sort of, like, I need to work out something as an error between the desired frame and the actual frame. So I need to measure the actual frame. So this is something that I need to include here. I need to include here the twist. So I need to measure the twist here. I already did. And I need to have here something related to the twist dot, which is also here. So this is the information I need. On top of that, the admittance control will require the force and torque sensor. And you also needs more information on the model. Here, I don't need to have any inverse or kinematics or inverse dynamics. There, I need to have the inverse kinematics and inverse dynamics in the way that's implemented. And there are alternative formulations. Okay, there's a vast literature on the topic. This is only we didn't even scratch the surface. Right? Yes.
6D damper and spring. Do they work when we thought of a problem flow and everything? Do they work in a similar way in the impedance control? I mean, is there a difference between telling the 6D spring and damper and a regular damper on how the concept of impedance control works?
Yes. The performance completely changes. Yes, and this is the surprise. So if I do this naively, as let's think of the naive way. I want 6 numbers to represent the error between 2 frames. What's the first thing comes in your mind? 3 positions minus 3 positions. What else? 3 angles minus 3 angles. Euler angles. I do this with Euler angles, and this is the Euler angle, the rate of Euler angles minus the desired rate of Euler angles, and I have the 3 positions, 3 velocities minus 3 velocities, and here 3 acceleration minus 3 acceleration, and 3 angular velocities minus 3 angular acceleration minus 3 angular acceleration. Works fine, right? You get weird stuff, and these are there are very nice videos, very classic ones in the handbook of robotics. I'm gonna share the chapter, inshallah. You can take a look at there, and they say if you do it naively with Euler angles, the impedance behavior will be a function of theta naturally. If you just do this idea of that, I want Q minus Q desired, so like an angular position minus the desired angular position with Euler angles, the apparent stiffness that the robot sees will depend on theta. Which means that if I want the spring, the spring will behave differently if it's in this way compared to that way. Okay? Which is a completely different problem, because now I need to have a set of gains for every orientation. And this is not how a stiffness works. Imagine that you have a spring, right? That like a 3D spring. So if I extend it this way, it should have a impedance behavior. If I extend it this way, should have the same impedance behavior. It's a physical spring. It should not change its behavior depending on the orientation. This is one of the manifestations of coordinates, and you need to do it geometrically consistent, but that requires a lot of time. Okay, you're gonna find a lot of literature there if you want to look at geometrically consistent springs. The surprise is that that a geometrically consistent spring is exactly the same as what we did it for a potential function, and you already know that. You just forgot it a long time ago. What is the force due to a spring? Minus K delta X. Where does it come from? Exactly, from the potential energy of the spring. You say I have a potential energy of the spring, and then the force due to a spring is equal to the gradient of this potential function with respect to the deflection. Does it ring a bell? Yes, for sure in physics. You definitely had that in physics. It's just that you moved on and you forgot about this idea of the potential energy, and you memorize that force due to a spring is minus K delta X. Force due to a spring is minus K delta X. I cannot extend that. But if I have here a 6-dimensional case, I need a potential function in SE3. How to do that? We saw an example on SO3. It can be extended to SO3 in many ways. So that's one. How can I calculate the gradient of it? You saw this is the same technique, but just I have now 2 spaces, SO3 and R3 inside of SE3. That's the second thing. The third thing is that how do I transform this gradient or this differential into a wrench? How do we do that? Very similar to what we did for SO3. The last thing is that how do we do the damping? The damping, by the way, is very easy. The Q dot is actually the V. The V is a twist, and it's a vectors, right? The twist is a vector. So I can have a vector minus a vector, but the only problem is that when you're dealing with twists is what? When I minus two twists, they should always be expressed in the same frame. If not, I need to do an adjoint. So this will have some sort of like a twist minus a joint multiplied by a twist, something like that. I'm only giving you just snippets here and there. Okay? There's no math. You see how much math that I'm hiding. Okay? It's for your own benefit, okay? And the acceleration is even worse. I'm not going to talk about the acceleration, okay? So let's stop, and if you have more questions, I can take them offline, okay? جزاكم الله خير. سبحانك اللهم وبحمدك نشهد ان لا اله الا انت استغفرك واتوب اليك.